This is problem number 6 on the sample test problems for test number 2. A population started at 10,000 people, and after 20 years it had doubled. A, express the population as a linear function of the number of years since the population was 10,000. So the way I'll handle this is to convert all this stuff into some ordered pairs. So I'm going to have x's and y's, where x is going to be the number of years since the population was 10,000. And y is going to be the current population. So initially the population was 10,000, so at some point there's a 10,000 as the y. And how many years has it been? Well, according to what I let x equal, it's actually been 0 years since we were at 10,000 people. And then it doubles, so that means at some amount of time we're at 20,000. And how many years did it take? It took 20 years. So now all we need to do is find the equation of the line that hits these 2 points. So first thing we need is the slope. So we'll subtract the y's. Divide by, subtract the x's. And we get 500. We should have a sense of what that 500 is measuring. It might help to think of what the units are. So the units here are people per year. So on average, if this is a linear function, then every year we gained another 500 people. So now that we know the slope, I think we've got everything. We'll go ahead and write the y equals mx plus b. Normally at this stage, you'd replace all those letters with numbers in order to find b. But this particular problem, the b is actually given. It's a gift. That thing right there tells you that b is 10,000, only because we know the y-intercept. It's one of the points. So y equals the slope we found was 500, x plus, and then the gift in this problem is the b is 10,000. If you didn't have that gift, then you would just plug in the x and the y from either of those points into this equation right here. And that would allow you to find b. Part B. When will the population be 40,000, assuming linear growth? So all we need to do is take that equation we just found and set the y equal to 40,000. Goal is to solve for x. We'll subtract 10,000 from both sides and then divide by 500. And so we get x is equal to 60. It'll take 60 years for the population to get to 40,000. Part C, express the population as an exponential function of the number of years since the population was 10,000. So you have a couple of choices here. Choice 1 is to write everything in terms of ordered pairs like we did, and then start with the basic definition of an exponential function. So one version of an exponential function is a times b to the x. And so what you can do is take the 2 points that are up at the top and plug them in for x and y. So using the first point, we get 10,000, that's the y, equals a I don't know times b I don't know raised to the x. The x for that point is 0. And so this is kind of nice because b to the 0 is 1. So immediately we get that a is 10,000. And so then we'll plug the other point in. So the y value of the second point is 20,000 equals the a we just found is 10,000 times b I still don't know raised to the x for that second point is 20. Things are getting a little crowded. Let's move that down a tiny bit. And so we have to try to solve for b. And so we'll first divide both sides by 10,000. And that gives me 2 is equal to b to the 20th. And it's common for people to feel like logs are the way you're going to solve this for b, but that's actually not right. You use logs when the unknown is in the exponent, but here the unknown is the base. So we're going to take both sides and raise it to the 1/20th power. Or said another way, take the 20th root of both sides. And when you raise both sides to the 1/20th, the right-hand side is just b. That's the goal. So in this case, we need to know 2 to the 1/20th. So we take 2 raised to the parentheses because the power is a fraction. So there's your b. So about 1.035. And that gives us our final answer here, which is y equals a times b to the x. A is still 10,000. B we just discovered is about 1.035 raised to the x. An alternative to this, a much quicker alternative, is to use another version of the exponential function. So we'll say or. We could use in red y equals, okay, it's the same a, but now because this is a doubling problem, actually it turns out you're going to multiply by 2 to some power, and the power is t divided by d, where d is the doubling time. So maybe you've seen that formula before. Even if you haven't, I'm hoping that you'll believe it right after we write down the specific values of the variables here. So in this case, a is still 10,000, that's the initial amount, times 2 is 2, p is t, and the doubling time in this case is, do we have here? Okay, so then up above, it said that it took 20 years for the population to double. And so for an exponential function, that doubling time is the same all the time. So we'll always take 20 years for the population to double. So there's another version of an exponential function that models this one. I guess maybe instead of t, we should have used x, but same idea. And then just to convince you that that's right, if we just kind of pull this out and write this as 2 to the 1/20th, and then raise to the t, I'm going to go ahead and type in 2 to the 1/20th on the calculator, or actually maybe you'll see that it's already there. So it turns into exactly the same thing we wrote in green. It's just kind of a more natural way, I think, to write the exponential function when you're given the doubling time. So either of those is fine. And then the second part here, part D, when will the population be 40,000, assuming exponential growth? Okay, so if you happen to believe that the doubling time is always the same, then since it took 20 years to double initially, then it's going to take 20 more years to double. So the population should be 40,000 after, let's see, after 20 years, we go from 10,000 to 20,000. And then after, so that's after one set of 20 years. And then after another set of 20 years, we go from 20,000 to 40,000. So the answer here, without really doing much algebra, is it's going to take 40 years. But if you want to do the algebra, then you pick one of your two equations. I'll do the one in green. And instead of the y, we're going to put 40,000. And now we'll divide both sides by 10,000. In order to solve that equation, because the variable is up in the exponent, we'll take logs. So I'll copy the equation, and then we'll put log in front of both sides. You can pick log of any base. The base of choice in calculus is ln, or I guess I should say the base of choice is e, so we'll use ln. Ln of 4 is just a number. The nice thing about logs is this property that says an exponent inside a log can come down in the front. So we're copying ln of 4, and the x from up above goes right into the front. And that's how we access something that is in an exponent. And then finally, to solve for x, divide both sides by ln of 1.035. Whatever we get will be our answer. We were hoping intuitively that it was going to be 40 years. Let's see if the funny logs that we've got here agree. Instead of typing in ln of 1.035 again, I'm going to use the number that's already up there on the calculator screen. So we'll do ln of 4, and then divide by ln of, and then here we'll do second answer. And that will just grab the 1.035 and more. And so we're hoping it's 40 years, and it is. And so last thing to say about this one is that, again, for exponential functions, doubling time is consistent. If it takes 20 years to double initially, then it will take 20 years to double all the time. Whereas for the linear function, it took 20 years to double initially, but then we saw over here, it took 60 years, not another 20 years. So it actually took 40 more years to double the second time.